We're going to get started into this lecture. So, just because I am still fairly unwell, we will only do this lecture today. So, what happened this week was that we had these two lectures, 7.1 and 7.3, that we used the pre-records from previous term for, and today we're going to do 7.2 conceptual modeling. The reason that this one was chosen to do this week is because last term the pre-record was actually done in person, and generally I don't think that in-person lectures do as well for recordings, but so that's why we're going to do it today, so we get a bit of an online recording example of it. So it should be a pretty light lecture. It normally only takes like 40 minutes, so we'll see if we can bash through it. For those of you who are watching it live, congrats for being here and being engaged. For the 95% of you who aren't, I hope that iteration 2 is going okay, or it's much more likely that when people are watching this that the statement is more that I hope iteration 2 went well, because you'll probably be watching it later on, but that's totally okay. This particular lecture is quite interesting, I think, and it's really born out of the idea that software, like, there's a bit that goes on between deciding you want to solve a problem and writing code is the short answer, and that's what we call design. We've seen that as part of the software engineering lifecycle. A critical element of software design, like getting that design of software right, is to be able to translate these complex system ideas into something high level and understandable. So, if you're sitting around and you think, well, I'd really like to build a system to help students figure out what rooms are free on campus, right? Between understanding the problem and setting yourself some goals for the problem and actually writing the code, you need to translate it into something and visualize it, basically. And the ways that we're going to look at this, we're going to talk about what conceptual models are. Basically, how do you plan things in software? And then we're going to take a deep dive in one particular type of conceptual model, which is a state diagram, because it's an easy one to talk about. And apologies in advance for my cough and my voice. It will sound particularly flat today. That's just me trying not to kill myself, in terms of too much energy. Okay, so question, what is a model? You've heard this term before, right? A model. Well, you got a few funny things, right? You might think of model trains, you might think of model boats, you might think of mathematical models, someone trying to model gravity mathematically. You might think of, runway models or something like this. But what we're kind of, getting closer to is also a model, but it's really a description of software. And this is what you kind of see here. This one's actually kind of a bit of a software model, and this is also kind of a software model. And this is also a model, not of software, right? It's a chemical model. I guess chemical. Would you call it a physics? I don't know. It's a science model of an atom from high school, probably. And there are lots of, don't know what that bit at the bottom is, but there are lots and lots of different ways of showing you what a model is, because you've probably heard about it in many contexts, right? You've probably seen other types of models, like the water cycle, right? This is a bit of a model. Or you've probably heard people talk about climate change and global warming as, they're like, the models show something. So what we're trying to do today is we're trying to dig into what all of this is really about, because these words come up. And a model is really just a simplified representation to assist in understanding something more complex, right? Makes sense. This can be interpreted in a lot of different ways, because you have things like, a mathematical model is meant to try and take something complex and abstract like the world and make it, real with numbers. A software model might be trying to take a complex piece of software and simplify it. A little model plane or boat is trying to take a big real world complex thing and make it small and simple. You got lots and lots of different things here. But they're all trying to do the same thing. Simplify and make more digestible. Now, a conceptual model is a particular type of model that captures a system in a conceptual way rather than a physical way. They tend to be diagrammatic or visual. So if you got like physical models and conceptual models, they're a little bit different. If we come back to our kind of slide back up here, this is a physical model. This is a conceptual model. This is a physical model. Maybe. I don't know if there's a... I mean, I guess, you know... I guess if the model is trying to represent something quite deep, like, you know, trauma or something, then it gets a bit conceptual. This is a conceptual model, that's a conceptual model, that's a conceptual model, that's a conceptual model, right? And we're interested in these more conceptual models today, and those conceptual models tend to be more diagrammatic or visual in nature. You know, so that means that they're not really like miniatures of something, they're more... It's something you could typically draw, is the short story. Examples of conceptual models are mathematical models like we saw before. Sometimes there are data models. Data models are just really diagrams or visuals to represent data. You could kind of think about the data.md that you did in iteration 0 as a bit of a conceptual model, but it was kind of, you know, it was a little bit of just text and stuff. You know, you could have drawn it diagrammatically, but it was a little bit of a summary of what you're doing at a conceptual level, right? Like someone who's not a programmer could probably make some sense of it. So you can model data, how data's stored. You can do domain models. This is something you kind of get into a bit more in probably Comp 2511 later on. You can do state transition models, which is actually what we're going to be looking at today, which is how does a program... how do you model a program that moves between different states, which is how a lot of software kind of moves, frankly, you know, so that's quite relevant. So conceptual models are also generally broken up into two different types. So remember, again, we've got like models, and then we've got conceptual physical models, and then within conceptual models, we're now digging into two types, which are structural conceptual models and behavioral conceptual models. And structural conceptual models emphasize the structure of a system. They show you how it just kind of exists as it stands, you know. They don't really tell you a lot about behavior. And a lot of conceptual models are structural in nature, right? Like if you have a look for a second at some of these again, or, you know, maybe something like, you know, this is a structural model. It just tells you, you know, what it's trying to achieve is to communicate to you how an atom like is. You know, this is just how it exists. This is how it's structured. So I'm just getting back to the slide. And two examples of conceptual structural models within software are class diagrams, which are like domain diagrams. Again, they're kind of covered in 2511. That's where you kind of look at the simplest way of explaining this without having gotten into it is that imagine if you had a way of trying to visually show all the different files you have in your project, like auth.ts and channels.ts, and how they relate to each other. You know, it's like a way of describing software functions and files is like a really, really dumb way of putting it. And then you have other things like entity relation diagrams, which you can go study in, like, I think it's Comp 3311 in the databases course, which is like a more souped up, intense version of, you know, think like data.md, but like blown out into like a formal way, you know, like an industrial size way. And you can see some of these diagrams. Like if I Google a UML diagram, you'll see something that these diagrams help try and describe software components. You see here something financial, banks, ATMs, accounts, customers, savings accounts, current accounts. If you look at something like an ER diagram, which is meant to represent databases more, then you start to get something that's actually showing you different things that are stored. You know, like this is some kind of review system, like users and posts and ratings, and users have names and birthdays and emails, and posts have images and descriptions, you know. So it's a way of like modeling the data that's stored within a system. So there's structural conceptual models, and then we have behavioral conceptual models, which are all about emphasizing the dynamic behavior of a system. So how does a system behave over time? And the two really standard cases for this are state diagrams and use case diagrams or user flows. And we're going to talk about use case diagrams and user flows next week. But today we're going to be talking about state diagrams because they're a really fun one to talk about. Now, before we get into state diagrams though, quick bit of recap. What are these kinds of models used for? Like the diagrams I just showed you, or the ones at the front. They can kind of, like, what they're used for can kind of be summarized into a few different buckets, which is like, they can either be used to predict the future, they can be used to understand the present, they can be used to make sense of the past, and they can be used to simplify things, and typically that simplification is like critical in all of it, right? So again, like you think about climate change models, well, climate change models are often about validating the past, predicting the future, and trying to simplify it a lot of the time. But most modeling involves some kind of simplification. It's just kind of inherent to it. This is a bit more of a formal take on what I just described. This is from an actual book that you can go and look at if you'd like to. Not book, paper. Something academic, where they talk about, the 4 objectives of communication with a conceptual model, like enhance understanding, conveying of details between stakeholders. Stakeholders are like all the different moving parts of a system. Point of reference for designers. Yeah, so this is actually an important thing I probably didn't mention, is like a lot of the time part of why we do these kinds of things, why we draw these diagrams and models, is for people who are going to actually go and make it real, So this doesn't make sense so much for something like an atom in science, but for some of those diagrams we looked at before, these things are actually really useful because you'll often have people go and design software and then larger teams might go and implement it. And it's like a really important reference, right? Sometimes you might have like thought about this or referred to this as like a blueprint for design. Can anyone hear the birds? The birds seem loud to me, but if the birds aren't too loud, then great. Just wanted to check. And just documentation, like code is often hard to document, and like even if you document, are they loud? Are the birds loud? Tell me if the birds are too loud. The documentation is really important because quite often you won't document code, It's just like no matter how hard you try and document code, someone who comes along and tries to make sense of what's going on with your code, it's just going to be like a real struggle, Like imagine sitting down with someone else's project backend that you haven't seen before and just trying to be like, what is going on here? And these kinds of models do a good backup for us in terms of like someone can look at this and be like, okay, I kind of understand what the software is trying to do because they've got that high level, right? It's all pretty intuitive stuff. Now, the particular type of behavioral conceptual model that we're looking at is a state diagram. And a state diagram is a diagrammatic representation of the state of a program that has multiple states. And it's a really simple diagram, which is also why I like it, and it's pretty fun to talk about because it essentially says that we're going to represent a system by drawing a bunch of circles, right? The exact shapes don't really matter as long as they're consistent. We go draw a bunch of circles for like, these are the different states that a system can be in, and then we're going to use arrows and notations to say how you get between those states. So in the cases here, if you're trying to create a state diagram for a door, like a door in your bedroom, say that you're in right now maybe, well, the door really has one of 2 states in theory, right? It's either open or it's closed. And if it's open, well, you can close it by going from an open state to a closed state. And if it's closed, you can open it by going from a closed state to an open state. Now, what did we say before? We said that models try and simplify representations. And this makes sense because if you've ever had a door, you'll know that your door is a little bit more complicated than that. Sometimes it's, like, has anyone ever been asked, do you want your door open or closed? And you say something like a little bit open, mostly closed, half open, open, or you stick the stopper in it, It's like there are more states than just this in reality. Maybe it's the door with it on its, those doors that like click into place and things like that. Maybe it is slightly ajar, just resting on the end, shut but locked, like you can go quite deep into this. But again, models are meant to be simplifications of the world around us. Now, does this mean that this is the perfect model? Is this the perfect amount of simplification? Like maybe. Sorry. Maybe. It kind of depends on what you're trying to achieve. There's no right or wrong answer to that. Because the answer is really just... It's like... where, like, and this is the thing with context, and this is true for software all the time, right? People get into arguments about, oh, is this language better than that language? Is C better than JavaScript? Is JavaScript better than MIPS or something? But at the end of the day, it's all about like why using it and how you're trying to use it. So it's like, well, what is this diagram for? It's hard to tell you whether this diagram is too simplified or not simplified enough, depending on what you're trying to use it for, you know? And if someone was like, oh, well, we're just trying to write a state diagram to help someone understand, you know, how they might want to manage their child's door in the house. It's like, well, maybe it's too simplified because there are other elements here that are at play. So, but that's a simple state diagram just to make a point. State diagrams, we said before, describe systems that have different states. Systems that have different states we call state machines. State machines are basically software that are made up of a finite number of states, as we just said. And the idea is that this piece of software is really just transitioning from one state to another. And some examples here are like UIs with different screens. And like, you kind of get this. Like, most software's like this. This slide thing you're looking at here is a state machine in a way, right? Like, we're moving between states. Like, here's a state, here's another state. Every time we change slides, it's another state. You can kind of view your own project backend that way as well, where, you know, you have an empty server and then someone registers and now you've gone from like an empty server to a server with more than one user, you know, like you kind of model it however you wanted. You could have a million different states or you could have just 5. Whew. Most I've talked in like 4 days. It's quite a trek. Okay. One good example of a state machine. One of the first state machines that left an impression on me, I've talked about this, I think, last couple of years. Robot Soccer. RoboCup, Standard Platform League. I'm not going to go too deeply into it, but let's have a look at these little things. Kicking balls around, right? So, see, look at these like little robots. Now, when I had a brief stint trying to program one of these, which didn't go very well, and I worked on a tiny part of it that was all around behaviors of the robots. The robots were structured like a state machine, and how they worked was that they were basically a series of states, like this. Different states, and those different states were doing different things. And this one might be like, I think it was like, you know, say, looking for ball. Let me make this bigger. Yep. Might be looking for ball, walking toward ball. There might be like, I think it was like lining up for kick. Kicking ball. I guess like kick back swing or something. You know, it's kind of like this. And the idea was that the way the robot was actually programmed was that it was always in a state, and in that state it had a particular behavior. So if you were looking for a ball, the robot was standing still and it was turning its neck and it was looking all around to try and find it. And you know what? If while it was looking for the ball, the only thing it could do from that state was go and walk towards the ball. Because if you're looking for the ball, you're not going to go and line up to kick it or backswing kick it. You're going to just be looking for it. So it would walk towards the ball. And you know what? When it was walking towards the ball, there was only really 2 things it could do. It would either get to the ball, where it would then line up to kick it, or as it was going to the ball, if it lost the ball, say someone came in and stole it, or maybe it lost vision of the ball, then as it walked towards it, it might have to start looking for it again. And as it was lining up to kick, you know, well, after it lined up to kick, it would go and like swing its foot back to kick it. Or if while it was lining up, the ball moved, it might have to say, look for the ball again. Right? And after it did its kickback swing, you know, if that didn't work, you know, again, it might go back to lining up or something. You kind of get where it's going. And then it would like kick the ball, and after it kicked the ball, it would go and look for it again. You know, you could kind of actually describe a software system like this. And a lot of software can be described like that, but that's essentially where this is heading. So if we then come down here and we look at this slide and we look at a parking meter example, you can kind of represent how, like think of an old school parking meter with like coins and stuff in the city, you come up to it and you start at this left-hand side here, and it kind of is like, hey, where'd you park, right? It's one of those ones where, you punch in a particular car spot. So it's like, okay, well, you get there and it says enter the parking bay number. So you type in, 62, like that. And then it's like, great. And we have a look at this. Well, there's only one inbound line out of this. So there's only one way you can go, which is that after you input the number, it says enter the duration. How long do you want to stay there for? So you enter like 2 hours, right? And then after, while you're here, you enter 2 hours. Either you input the 2 hours or you click the cancel button. And if you click the cancel button, you go back to the start screen. That makes sense, right? Like, how long do you want to stay here? Enter it or cancel. So there's 2 ways out of there. And then once you've entered the input, it's like, okay, parking bay 62, 2 hours, please insert the money. So now you're in this state. And now one of 3 things can happen. Either you click cancel and the coins are rejected, and you start again. Or you insert a coin, and if you insert a coin, you come back here. Or at this point, there's no more coins to insert and you finish and you go back to confirm. And then from like confirm is in like a final, like, are you sure you want to go ahead with this? Right? And then from that, you can either like click OK to like finish up and get it all confirmed and get your ticket, or you can cancel it, which winds it all the way back, right? So, they're just the different ways you can do stuff. Now, that should make sense too. The interesting part about this, actually, and have a look at this diagram. So this diagram's slightly annotated because the point of this parking meter diagram is to really articulate how simplified some of these things can get. Because if you really think about a parking meter, you can ask some interesting questions. And the question that was asked between this diagram and the next diagram was like, well, how do you represent a timeout? Because if I go and enter parking bay 62 in it, and I don't click cancel, or I don't insert any numbers, it just kind of stops, just kind of ends. It's like, all right, well, let's annotate it further. Cancel or 5 minutes elapsed. Cool. So all we've done here is instead of saying cancel, we say cancel or 5 minutes elapsed. And here we're like cancel or 5 minutes elapsed, and then the coins are removed, So you can just kind of keep annotating this, and we've done this at the top. So at each step, there's like a, a timeout element to it. Now, there's still kind of limitations of this, things that might not make sense, or, what happens if you insert a coin that's the wrong size? You insert, like it says you need to enter 80 cents and you put in $1. Well, it's probably going to reject the dollar, but that's not represented here. How would you represent that, So you insert a coin. Well, should you create a new state, a new circle, where that new circle is like insert coins that are rejected, or do you just create a line that says coin inserted that's wrong? You know what I mean? Like, and this is like, I think this is kind of one of the fundamental challenges of getting a good state diagram, is that everything you want to represent, you have to ask yourself, should this be represented as a state in the state machine, or should this be represented as a transition between 2 states? Is rejecting a coin its own state, or is it an action? Well, entering a coin that's wrong is an action, but where does that take you? If it just takes you back to insert coins, how do you represent that? So again, if I drew it here, copy image, see if I can just do this, right? If I just tried to draw this here and I was like, well, yeah, it's probably just another thing. And then what am I going to write here? Like on this line, imagine that's on the line I just drew. Coin insert, but wrong size, so rejected. It's a little bit clunky, isn't it? It's probably okay, but that's one way to do it, for sure. So we're going to do a quick activity because we're nearly at the end here. Well, it's not super quick, but the activity is, can we model the Opal card system in Sydney? So if anyone has ever been to Sydney, traveled to Sydney, right, which, most of you have probably in some way, how do we represent Opal, or like, just Sydney Transport? I don't know. I haven't used Opal in years because I've been using my credit card thing. So how would you try and describe how the system works. And what I mean by this is, you know, tap on, tap off, all of that kind of stuff. It's a fun topic for me because I've always loved reading the rules about, you know, Sydney transport and stuff. How would you start? We got 11 people here. Someone give me a bit hot, so forgive all my shirt picking. How would someone start this? What would you do? What's the first state you'd have? Not tapped on. Okay. So Daniel says not tapped on. Let's try that. I'm going to use these. Oh, it's a bit ugly. That's a good first state. Not tapped on. Okay, and where do you go from not tapped on? Well, okay, well, you tap on, don't you? So let's make... I'll help you out, you know. But, like, keep adding. Please keep adding things. So, like, after you know... I might draw this further away. You know, if you haven't tapped on, well, you can tap on, right? There you go. Tap on. Then, you know, so we're getting a good split here between, like, states describe moments, you know, and the lines describe actions. So what would you do next? Someone, I'll help finish it out and stuff, but, like, someone give me some more. What else would we add? Help me out. Tap off at a different location. That sounds like an action. But where does that take you? Cancel tap on? I guess, I mean, let's just... Okay, well... Let's just draw two. We're going to have to unwind a few things here. But let's say one was like cancel tap on. And the other one is tap off at different location. Now already, like, you can kind of start to feel this getting a bit complicated, right? Because, you know... You just get into weird areas. Like, you can start asking yourself questions already about, oh, this doesn't really tell you anything about how much it costs. Which is like a little bit of a problem. Or like tap off at a different location. Okay, well, what happens if you tap off at the same location? What happens if you tap off at the same location 4 hours later? Well, that's not a cancel. Now you're just tapping off at the same location. Because the way the trains work in Sydney is that you only it's only cancelled if you tap off within 15 minutes. So now you tap off at the same location. It's like, okay, this is starting to get a little bit unruly. Dylan says insufficient funds, and Adrian says that as well. So it's like, okay, well, if you're not tapped on, you can try and tap on, but then you have tap on, not enough funds. Sure. Jed says deduct money. Now, this is where it gets more fun, right? Because it's like, all right, well, if you tap off at a different location... Do you put deduct money there? Do you put that as a state where all deduct money takes you back somewhere? You know, it kind of gets a bit further. So let me just complicate this a bit more for you. So couple of important rules to do with Sydney transport. This is just fun little... Is it Opal rules? I don't know what it's called. Opal benefits? I don't know. So, oh, damn it. Okay. I don't like this. I'm a little bit worried. So, some simple rules with Opal, right? Or like the network. If you tap off at the same place you tapped on within 15 minutes, you aren't charged anything. If you tap on again after tapping off somewhere less than an hour ago, your trip is just extended, right? So they're two simple things we can start with. So now it gets interesting, because now we have to think about, well, how can we intelligently describe this? Well, you got this 15-minute problem. Well, what you could do is you could say, well, there's not tapped on, and there's tapped on within the last 15 minutes. So now what happens is someone taps on from not tapped on, like that. And now you kind of have an easier way to represent this, because if you're not tapped on, well, you can tap on. And if you tapped on within the last 15 minutes, you can tap off, cancel, you know, no charge or something. But if 15 minutes elapses, then you probably automatically kind of maybe go into the next one, which is call it like, you know, tapped on for more than 15 minutes. And this one is just like automatic after 15 minutes. Something like this, right? And we've still got those states you guys mentioned before, where you have this one here, which is like tap on insufficient funds. Insufficient funds. Okay, then it's like, well, if you tapped on for more than 15 minutes, well, you can now tap off, right? Surely. Okay, well, what happens if I tap off? Well, this is where it gets tricky, because like, if you tap off now, you're not necessarily not tapped on. Because if you leave home right now and you tap on a train, you're like fresh. Whereas if you tap off a train and then you tap off another train within an hour, if you've been in Sydney at all, which many of you have, it's like you extend your trip. So there's actually kind of like a weird state over here, which is like a it's like not tapped on, but mid-journey, you know? And that's the kind of thing where, okay, if you've tapped on and it's been more than 15 minutes, if you tap off, then, you know, and this is also where your charge, say, we'll make that. And if, so say you catch a train from, you know, Hurstville to Central in Sydney, you tap off. Well, you come into this not tapped on, but you're still in the journey state for an hour, like we set up here. And now what happens, well, let's say you don't do anything after that hour. Well, after that hour, you will just automatically get sent back here to the start, which is, you know, like an hour passes. But if you do tap on, right, within that hour, then you come up here, which is that you've tapped on again. And this within the hour is like if you tap on within hour, you know? Now, I'm not going to take this much further, but I'm trying to articulate to you a bit of a balance here, because like sometimes stuff's really hard to represent. It's this question about, you know, this doesn't do a good job of representing dollars. You know, it's not a financial model. It's really like, it's not a financial, it doesn't model the cost of this very well. It really models your trip validity in a way. Like it models whether, you know, whether you're on or off the train. This might be something that, you know, like, oh, you know, you've been on a train and a train inspector come and like taps your phone or something. And it's like, well, you know, a system like this is, you could model how those things say it's okay or not okay based on this, right? Pretty easily. Cool. Any questions about this? We'll move on to the last slide, but I think this kind of really starts to drive the point home a little bit as well. Just give everyone a minute in case you have questions. Sorry about all the coughing and the faint sounding everything. I'm going to keep moving on just in case. We'll stop if someone asks a question in the next 10 seconds. So the last thing was just, this is just a little bit of fun. It's just a story I like to tell. Because I think it's a really interesting, probably still one of the most interesting examples of like a university level engagement with a conceptual model. Basically, there is a race, uni students race, every couple of years. They all race from the top of Australia to the bottom of Australia. It's about 3,000 kilometers, and they all race solar cars from the top to the bottom, right? So lots of different teams from around the world. They build these things and they race them from the top to the bottom. it's obviously a mountain of work to build these things. They're very complex mechanical and electrical feats. But a really interesting question is that you have 6 days to do this drive, and you have, depends on the rules, but just to simplify it, you have a battery of a certain size, right? Just like a car. A car's got a fuel tank. Fuel tank's only so big. And you have to make a decision as to how fast to go. Like, think about this too, right? Let's imagine you're driving from Sydney to Melbourne or Sydney to Canberra, and you have a half tank of fuel, right? It's about 300-ish kilometers. But you need to be the first one there. If you drive too fast, you run out of fuel. Because the faster you go, the more fuel you use, right? Because when you go faster, it's like anything in life. You go faster, you got more wind on you. There's a cubic relationship with the wind, or quadratic, I can't remember, that slows you down. But if you go too slow, you'll get there last. So it's a pretty simple trade-off. And it was a peer of mine, a student, in 2015. They designed a conceptual model that they then expressed through coding, right? They wrote it in Python, a language similar to JavaScript. And you can follow some links there if you're really interested in more. But basically, all this tried to do was model the car. Model the car as it drove across the country. This isn't like a toy model, like a miniature of the car. This is saying, well, you know what? It's actually really, really complicated to figure out how much energy a car uses, right? Like, think about you on a bicycle. How much energy do you use on a bicycle? Well, it kind of depends how pumped up your tires are. It depends how good the bearings in the bike are. It depends which way the wind's blowing. It depends how hot it is, because the hotter it is, the more tired you're going to get, because you're going to sweat more. Depends how much sleep and like your physical state. It depends on your strength. Some of these things are quite constant, like you have a strength, and that's pretty similar every day. But the wind direction kind of comes and goes, and wind's very complicated, right? And like, how can you even predict we can't even predict the weather generally. So how can we predict how much energy you're going to use exactly on this particular cycle? And it's the same kind of thing with a car. So there's all these complicating factors, like the car is driving. Is the wind coming from behind, which is helpful, or is it coming from the front, which is bad? Is it coming, how fast is it coming? How much sun is coming down onto the top of the car? How much cloud cover is there? Because that affects the sun in a very complex way in terms of how much hits the solar panels, because they're all solar cars. What's the road like? Driving uphill is quite taxing, and it takes a lot of energy. Driving downhill is pretty easy. The faster you go, obviously, the more energy. That's kind of like the parameter of the function in a way. But how's the car oriented? Because if the car's facing one way, if the roof's not flat, it's going to pick up different amounts of sunlight, right? And then how heavy's the car? There's more stuff than this. And the way that this student designed it was they basically broke up the entire, it's a 3,000 kilometer, so like 3 million meter drive. And they broke it up into like 10,000 intervals. And each interval was, say, 30 meters, I guess. Yeah, 30 meters long. So they said, like, think about sampling from high school. Got like music sampling or whatever. They're like analog to, how is it? Digital, analog. I can't remember. Analog to digital sample. Yeah, you remember learning this kind of stuff in school, where they'd be like, oh, if you take like a real world signal, you have to, it's kind of modeling it as well, right? You're like simplifying. You're like, well, let's just like simplify this down. So a very similar thing was done, which said, well, it's impossible to know what, the elevation of the road is every single meter, that's very complicated. So let's actually just say, well, you know what, this 30 meters of road is exactly the same. It's exactly this elevation perfectly. It's exactly like this orientation perfectly. We're going to assume that for this 30 meters, say, the sun is going to be shining at exactly this brightness. And then all this model was saying, let's break up that trip into 10,000 pieces. And then let's, for each piece, calculate how much energy the car has to use. Let's sum it all up, and then we'll get a distance, right? It's like, again, in a car, it's like, let's just break that trip to Canberra up into 10,000 pieces, figure out for each piece, for each 30 meters, for instance, how much fuel do you use, and then see if you have enough fuel to get there. And if you don't have enough fuel, slow down and check again. you know? And then if you have way too much fuel, speed up and check again. So it was essentially just a piece of code that was designed to really just simplify what was going on by modeling it, right? And it's a really cool example of a conceptual model because, again, it's taking something that is complex, it's making it simpler, it is sampling the world, it is typically ignoring things. There are always lots going on here that don't make sense. Like, for instance, the temperature of your car tires affects how efficient they are in ways I don't fully understand. The humidity affects all these things, you know, but you kind of ignore those things because they're too complicated. It's like when they model the economy. They don't take into account every single little thing. They simplify it. Anyway, this is a bit of a random story. But the point was just to show you this is another, like, we talk a lot about conceptual models and it's not a new idea. You're kind of all very familiar with this because you've seen it before. You probably just haven't given it a name. So thank you. If you do have any feedback, please fill out the form. It's always welcome. Yeah. Thank you, everyone.